Alright, so now we're going to move on to the second of three basic cases for the method of undetermined coefficients. This case is actually easier than the first, and it involves linear equations where our phi of x is just some multiple of an exponential function. Again, keep in mind the functions we generally work with are polynomials. Other algebraic functions, maybe square roots and things like that, but algebraic functions like polynomials are commonly used, and the reason for that is we'll talk more about that in analysis class, but they are used to approximate various other continuous functions. The other kinds of functions we consider are trigonometric functions and exponential functions and logarithms. So we're going to look at exponential functions. So we have our phi of x is negative 9 e to the 5x. So that's just, again, some multiple of e to the 5x. So a good guess for what y sub p is going to be a multiple of e to the 5x. Now, or a is some unknown coefficient that we have to determine. So why is this a good guess? Well, just think about it. If I differentiate yp, it's still going to be what we're going to get is a multiple of e to the 5x. And if I differentiate it again, it'll still be a multiple of e to the 5x. So with this guess, if we plug yp into our linear differential operator here, we're going to get three terms which each are a multiple of e to the 5x. We can combine them and we'll have a single term which is some multiple of e to the 5x, and that multiple is going to involve the constant a that we don't know. If we set that equal to the negative 9 e to the 5x, we can figure out what a is. So we plug in our guess. Just have to compute these derivatives. Second derivative, we get 25 a e to the 5x, because each time we differentiate yp, all that we're really doing is using the chain rule, and that 5 is going to come down as a multiple each time. So we get 25 times a e to the 5x for the second derivative. First derivative is going to be 5a times e to the 5x. We have a negative 6 in front of that term, so we get negative 30. And then we just add to that finally 8 times y sub p. And we notice that we can just combine all these, and it reduces to 3 times a times e to the 5x. So we made our guess using knowledge of differentiation and exponential functions, basically. And we now know that if yp is actually going to be this particular solution to our equation, then this left side we just showed is equal to 3 times a times e to the 5x. So that must give us this equation, and if we solve that for a, we see that a is negative 3. And that means our particular solution is negative 3 times e to the 5x. So these exponentials are all done in the same way. It doesn't matter, as long as you see some exponential here, some multiple of it, your guess is going to be some multiple that you don't know, a, times the same exponential function. So if it's e to the 10x, you use e to the 10x. If it's e to the minus x, you use e to the minus x. So let's go through an initial value problem to go through our entire process with this kind of example. So we have a second order linear differential operator applied to some unknown function y, and we want to know what that function y is so that when we plug it into that differential operator, we end up with negative 10 times e to the negative x. But we also want to impose the conditions, the initial conditions, y of 0 equals 0, y prime of 0 equals 2. Again, the term initial just typically refers to when your inputs are for the conditions are 0, and this is commonly used when input is time. Even though we're using x here, it doesn't really make a difference, but that's what an initial condition is. When you're given conditions like y of 5 equals something, those are typically called boundary conditions, because maybe the context of your problem is that this function y has a domain of some interval, say 2 to 5. So you may have a condition at 2 and a condition at 5. But this is what we call an initial value problem. So again, from our general presentation of solving linear equations, we know that our solution y has two parts. The homogeneous solution, or y sub h, solves the homogeneous equation, where we just make the right-hand side 0. That's what we just got done talking about, how to solve that using characteristic equations and roots of the characteristic polynomial. And yp is going to be one particular solution of our equation. Again, remember what we just did in the previous example. We found a particular solution to something like this. But that particular solution doesn't have any unknown constants. It's a specific function. So this y sub p may not satisfy the initial conditions we're given. It does satisfy the equation, but not the initial conditions. So that's, again, why we also come up with the general solution for the homogeneous part and add it to y sub p. Because this y sub h always is 0 when we plug it into our linear differential operator, so it doesn't change the fact that because y sub p solves our equation, so does y, because y sub h just gets zeroed out by our L of y. But y sub h will have constants in it, which we can then use the initial conditions to determine what those constants are. So first we determine the homogeneous solution y sub h. So our characteristic equation given here. This is easily factored. Again, if you have a product of two numbers equal to 0, then either one is 0 or the other is 0. So this gives us the two real solutions, r equals 4 or r equals 2. And from our first case, from the second order problems of what we've been talking about, we know that y sub h has this form. This is the sum, a linear combination of two exponential functions. One is e to the 4x and one is e to the 2x. So here's our problem. We've already determined the homogeneous part of our solution. Now we want to find the particular solution. Because our right-hand side is just a multiple of some exponential, we define our y sub p to be some multiple of that exponential. And this a is just the unknown constant that we have to figure out. Again, we just do that by plugging y sub p into our equation. So again, every time I take the derivative of this y sub p, all I'm doing is changing the sign by the chain rule. The minus 1 will come down each time. So two derivatives just gets us back to a times e to the minus x. One derivative will be a negative a e to the minus x, but we have a negative 6 in front. So those two negatives cancel, and that's why we have a plus 6. Then we just add to that 8 times our y sub p. And we see we add those up. We get 15 times a e to the minus x. So all we have to do is set that quantity. If we want y sub p to be the solution, we just have to set that quantity equal to our minus 10 e to the negative x from our equation. And that'll tell us what a is. So in this case, a is negative 2/3. So we know that y sub h has our general form with two constants that we don't know, but we can determine by our initial conditions. And our y sub p is the part that's actually making sure that our solution y is actually a solution to the differential equation part of the problem. Again, this all relies on linearity. The linearity is what allows us to add these two functions, one which solves the equation and one which doesn't solve the equation but does get zeroed out, so it doesn't affect that y is a solution. So that's our general equation. So we now move on to determining C1 and C2 from the initial conditions. Again, it's a second order. We want to get a unique solution. We're going to have two constants to determine, so we're going to need two initial conditions to determine them. Since our second initial condition involves the derivative, we're going to need to compute the derivative of y, which we have here. Again, it's just differentiating exponentials and using the chain rule. So the first equation, y is 0 equals 0, we just plug that in to our equation for y. So 0 is y, and 0 is x, reduces to this equation. This equation involves both C1 and C2, so we'll just solve it for one of them. if we solve for C1, we see how C1 depends on C2. It's 2/3 minus C2. So we'll just keep that for now, and we'll move on to the second equation. So the derivative of y at x equals 0 is equal to 2. So we plug that into our equation for y prime, and we get 2 is equal to 4c1 plus 2c2 plus 2/3. But we know that c1 is just an expression involving c2, so we can plug that in. And now we just have an equation involving only c2. And that's easy to solve, and we can see that c2 is just 2/3 from that. Now that we have c2 is 2/3, we can go back to the first equation, plug that in to see what c1 is, and we see that c1 is 0. So this is a unique solution to the system of equations, because this is a system of equations with two unknowns, c1 and c2, and because it's the same number of equations and unknowns, there's either going to be no solution or a unique solution. So if we find a solution, it is unique. So this is a unique solution. That tells us what our y is. So remember, y is going to be c1, which is 0. So the e to the 4x term actually doesn't exist. It's not there. And c2 is 2/3, so that's why we get 2/3 e to the 2x. And then remember, our particular solution was minus 2/3 e to the minus x. So that's here. So there's a solution, a unique solution to this initial value problem.